Welcome everyone to Macroeconomics Session 5, ISLM model, formal analysis. The first thing we want to see in this video is systems of linear equations and Cramer's rule. Static macroeconomic models can be represented as system of equations. Solving this system of equations for endogenous variables yield the equilibrium. So you may remember in our previous exercise sessions we had defined IS and LM curve function, which is given by these two formulas displayed on the screen. So our IS is represented by y is equal to CO plus C1 y minus t plus B0 plus B1 y minus B2 I plus government expenditure G. And our LM is represented by M over P is equal to DO plus D1 Y minus D2 I. So in these two equations, as you can see, there are two endogenous variables, Y, our income level, and I, our interest rate, because we were also using them as X axis value and y-axis value when we were drawing our ISLM curve. So these two variables are endogenous variables. The first thing we have to do to solve this system of linear equations is to gather our endogenous variables on the left-hand side and leave our all exogenous variables on the right-hand side of the equation. So starting with our IS curve, we had said IS is CO plus C1 multiplied by y minus t plus B0 plus B1 y minus B2I plus G. So as you can see from this equation, my endogenous variables y and I are appearing on both sides of the equation. So our plan is to gather these endogenous variables to the left-hand side and leave the other exogenous variables on the right-hand side. To do so, we would first get rid of the bracket in the second part of the equation by multiplying C1 with y and C1 with t, and the rest of the items would remain the same. So what we want to do, as we have said, is to gather our endogenous variables to the left-hand side. So these three equations parts should be sent to the left-hand side of the variable so that we would have both y and I on our left-hand side. So this is to say, I would take all these three parts of the equation to the left-hand side, and this would give me an equation which looks like y minus C1y minus B1y plus B2I is equal to CO minus C1t plus BO plus government expenditure G. So if I take y as a common for these three items, I would have 1 minus C1 minus B1 plus B2I is equal to CO minus C1T plus BO plus government expenditure G. So with this equation, we have just managed to gather our endogenous variables to the left-hand side of the equation and to put our exogenous variables on the right-hand side of the equation. So this is again the IS curve. Moving on, we would look at our LM curve, which was given as m over p is equal to dO plus d1y minus d2i. Here again, as you can see, these two variables are appearing on our right hand side, so we can take them to the left hand side and write them as they are, and we just have to subtract dO from both sides of the equation, which would give us m over p minus dO. So this equation again gives us a simplified form of our LM curve, where we have our endogenous variables on the left hand side and exogenous variables on the right hand side. So these two systems of linear equations can be solved using a matrix representation, and for that these two systems of linear equations can be written in a matrix representation by saying a11 multiplied by x1 plus a12 multiplied by x2 is equal to b1. So x1 and x2 are our endogenous variables, whereas b1 is the matrix of our exogenous variables. For the second equation, we can also write a21 multiplied by x1 plus a22 multiplied by x2, which would give us b2 in return. So now, as we can see, we have our two endogenous variables x1 and x2 on the left hand side, and we have our two systems of linear equations. So this can be solved by the concept of linear algebra. For that, we need to convert these two equations to a matrix representation. To do so, it's just taking the first values of a11, a12, a21, a22. This is to be considered as one matrix multiplied by another vector matrix x1 and x2, which would give us b1 and b2. So this linear algebra representation or matrix representation would help us to solve for x1 and x2 in a linear system of equations. So this can be written as, we can consider this as a matrix called A. We can consider that as a matrix called X, and this can be considered as a matrix called B. So to solve for these coefficients of the exogenous variables and the endogenous variables, there would be a solution for this problem, and we would get an equilibrium by solving this system of linear equations. This is done by first rearranging the endogenous variables as we have just made to the left hand side, and then we can also use the Gauss method. We can also use calculating the inverse of our matrix A and multiplying it for both sides. So if I multiply the inverse of matrix A in both sides, I would have an equation which would look like this. So any matrix multiplied by its own matrix would give us 1. So this A inverse multiplied by A would give me a positive 1 figure. So this would lead to an equation which says X is the inverse of matrix A multiplied by B. So if you convert these equations into the matrix representation that we have just seen here, you would be able to solve for x1 and x2. The most well-known approach to solve such type of equations is Cramer's rule, which gives us a solution for x1 and x2. We have just written our matrix representation of our equation by saying A11, A12, A21, A22 as a matrix multiplied by the vector matrix of x1 and x2 is equal to B1, B2 matrix. So the Cramer's rule says first it takes the determinant of our matrix A. A determinant of a matrix A is represented by not the curve bracket here, but we should write it as a straight line. And if I write determinant of a matrix A, I can write it in a way that looks like this. So the difference here is this is a matrix, but this is a determinant of matrix A. And if I want to solve for this determinant, what I have to do is I would just make a crisscross multiplication first. So I would multiply A11 multiplied by A22. So I'm just taking these two diagonal matrices first, and I would put a minus here, and I would just multiply these remaining two diagonals. So A12 multiplied by A21. So the resulting number would give you the determinant of our matrix A. If you know how to calculate the determinant, then the Cramer's rule would be an easier option for you to work through the matrix representation that we have just made. In the Cramer's rule, the solution for x1 is given as first determinant divided by another determinant. So on the denominator, what we always put is the determinant of our matrix A, which I have already calculated here, but I would write it again. A12, A21, A22. So here we are trying to solve for x1. As you can see, x1 is appearing here, and the corresponding x1 values are these two elements, A11 and A12. So what I would do as first determinant of the nominator here is to replace the x1 values with my B matrix. So the x1 values were A11 and A21, so we would replace them with B1 and B2. And the rest of our matrix remains the same, so A12, A22. As I have said, the determinant can be done by doing a crisscross multiplication and then subtraction of the diagonal matrices. So I would do like B1 multiplied by A22 minus A12 multiplied by B2 divided by A11 multiplied by A22 minus A12 multiplied by A21. So this gives us the solution for our x1. In the x2 case, we are also considering two determinants. As I have just said, we have replaced the coefficients of x1 in the matrix representation for x1, and now we have to take the coefficients of x2 for our matrix representation and replace them with our B matrix. So this is to say, here on the second column of our matrix, I would write B1 and B2, and the first values would remain A11 and A21, Our denominator remains the determinant of our matrix A, so it remains the same. Again, when we solve this, we take the diagonal multiplication, A11 multiplied by 2, subtracted to B1 multiplied by A21, and this again is to be applied for our determinant of our A matrix, which is already calculated in the above state. So this gives you a solution for x1 and x2. If you want to solve for these numbers, you would then use the Cramer's rule to solve for x1 and x2 as mentioned earlier. Now we would look at a numerical example which would give you an idea of how you can use Cramer's rule to solve for two systems of linear equations. So we would have 3x1 minus x2 is equal to 2. That is our first linear equation. The second linear equation is 2x1 plus x2 is equal to 8. Here you have two endogenous variables x1 and x2, and you are asked to solve the values of x1 and x2 using the Cramer rule. So first thing you have to do is you put a matrix representation of all the coefficients here. So I would have 3, I would have minus 1 as a coefficient of x1 and x2 for the first equation. For the second equation, coefficient of x1 is 2, coefficient of x2 is 1. Here I would have x1 and x2 as a matrix, which would give me another matrix of 2 and 8. Yeah, for x1, we would like to develop determinant matrices first and then try to solve them. As I have said, the two coefficients of x1 are 3 and 2, so I would replace the two coefficients of x1 with 2 and 8 in our denominator, and then minus 1 and 1 would remain the same. And this is again, please take care that a determinant is indicated with a straight line while a matrix is indicated by the curvy bracket. So the denominator remains the same, so we would have 3 minus 1, 2 and 1. Taking the diagonal terms, 2 multiplied by 1 minus 1 multiplied by 8, and for the denominator we would have 3 multiplied by 1 minus 1 multiplied by 2. So the first equation would give you a value of 10, while the second equation will give you a value of 5. So this would give us a final value of our x1 to be is equal to 2. Similarly, we would construct the values of x2 by determining the determinant matrix. As we have said, the denominator remains the same, but for the numerator we would have 3 and 2 in our equation. Minus 1 and 1 were the coefficients of x2 in equation 1 and in equation 2. So we would replace them by 2 and 8 here in our determinant identification. So here again, I would take the diagonal terms, 3 multiplied by 8 minus the other diagonal term, 2 multiplied by 2, divided by 3 multiplied by 1 minus 1 multiplied by 2 which would give us again a value of 20 divided by 5, which is equal to 4. So we have just seen how we can use a Cramer rule to identify the two endogenous variables. And in the next exercise session, we would use this basic Cramer rule understanding to come up with our two endogenous variables in the IS and LM model, y and I to be exact. And this is intended to give you a quick overview of what a Cramer rule would look like. And with this, I would end the introductory session of session 5.